For the today's session, here is our speaker and Professor Additive Kumar sir. He is our head of the department and professor in the Department of Mechanical Engineering at NIT Warangal. It's my pleasure and honor to introduce the speaker. Professor Additive Kumar sir did PhD from Osmania University in the year of 2008 under the guidance of Dr. Sundarajan. He is a well-known person, the former director of BrahMos, DRDL Hyderabad, and he did PhD in the area of simulation and characterization of aluminum alloys weldments. And his research contribution in this, the direct application of BrahMos aerospace missile, which was recently handed over to the defense. He has more than the 20 years of teaching experience and 12 years of research experience, and his research areas include the friction stir welding, processing, IT manufacturing, electro discharge machining, and fabrication and characterization of micro and nano composites. He has guided more than 8 PhD students, and 7 PhD students are undergoing in the progress. And he published more than 100 research articles in various reputed international journals and conferences. And he has published more than 10 book chapters. And also, he is a very leading researcher in our the Department of Mechanical Engineering. Now, I would like to invite the speaker, Professor W. Kumar sir, to deliver the session on this the solid state, the welding process, solid state, the additive manufacturing process. That is how the solid state based 3D printing process are going to be happen in this additive manufacturing process. Very good morning, sir, and I would like to hand over the session to you, sir. Thank you, sir.
Yeah, thank you, Dr. Manjaya. Nice introduction about me to the participants. Okay. Yeah, is it my screen is visible?
Yes, it's visible, sir.
Yeah, very good morning to you all. Today I'm going to talk about on non-beam based additive manufacturing, which is generally used for defense and aerospace applications. My presentation is towards metal additive manufacturing. Those metal additive manufacturing components used for mainly defense and aerospace applications. That's why I kept the title non-beam based additive manufacturing and, uh, and the defense applications. My talk is on introduction to additive manufacturing. It is slightly different from what other speakers are dealt during last couple of days. And again, I'm talking about non-beam based additive manufacturing. Uh, in this, we are working on friction stir additive manufacturing because we have a facility. So initially, we are working in friction stir welding. Then, after development of additive manufacturing, we can also develop the components through these techniques using friction stir welding principles. We can also develop the additive manufacturing components. So in this, mainly two types. One is additive friction stir deposition. Other one is all uh, friction stir additive manufacturing. So the detailed discussion in coming slides. Then one more important additive manufacturing, ultrasonic additive manufacturing. So which is very useful for especially electronic applications where so once you are friction stir welding or additive manufacturing using powder based or FDM process, the properties are going to change. But in electronic devices, we mostly do not change the properties even if you are applying the process. So that leads to improvement in your technology for certain applications. So this ultrasonic additive manufacturing is very useful in that area. Even before and after the process, there will not be any change in the material properties. So that is the greatest advantage to the industrial applications. Uh, then another process, wire arc additive manufacturing. So this also we have uh, many faculty like Manjaya, me, and Dr. Shivaraman and Dr. Davidson is also working in this area. So this is more prominent area where you are going to build the large size of components without much difficulty. Uh, Recently, total entire ship building manufactured through wire arc additive manufacturing facility. So you can reduce a lot of time to complete your product. So here, just you can use arc as a source for melting of the materials. So this I can classify it under non-beam based additive manufacturing. And coming to the beam-based additive manufacturing, direct energy deposition process and powder bed fusion process, hybrid manufacturing. So this part I can be discussed in the next session. So today I'm strictly based on non-beam based additive manufacturing related to friction stir additive manufacturing, additive friction deposition, and ultrasonic additive manufacturing. Per time permits, I can also extend wire arc additive manufacturing. So basically, you can see the various manufacturing process, how you are going to develop the component. So the based on the customer requirements, you can generate the component. So whatever it form, it doesn't matter for the customer end point of view. Whereas mechanical engineering point of view, we have concerned the properties, how the properties are enhanced from one process to other process. So for example, if you want to develop this kind of object through any process based on the customer requirements. So initially I can go for subtractive process where unwanted material can be removed by milling process so that I can able to generate this kind of object. So that's why you have to remove the unwanted material. So the material before and after may not be the same. So after the milling process, the volume of the material is reduced, then it is comes under a subtractive manufacturing process. Whereas coming to the formative process, same component of required dimensions you can also produce through forming process. You can push the raw material through a die. So depending upon the die configuration, you may get a different cross section of the component. So here there will not be any change in volume before and after the process. Only you are going to change the shape from initial to final one. So depending upon the cross section, it may varies the length or any other features, but volume should be same. So now coming to the other area is additive manufacturing. So same component I can generate through additive manufacturing. by depositing layer by layer. So every time you are adding the material to the previous layer or substrate initially, then it is a positive process. So your volume of the material is with respect to the time, production time is increasing. So that's why it is comes under additive manufacturing process. So the definition of additive manufacturing is a manufacturing process in which functional parts can be made by adding material without using special tools, jigs, or fixtures. So already you have experience in the laboratory sessions. So without need of any additional devices, you can also generate a complex structures because every 2D geometry is a unique type. So you can print that 2D object or 2D geometry, then you can build one over the other. Automatically, you can get different pictures. So it provides tremendous advantages compared with traditional subtractive manufacturing, especially reduce the lead time and also wastage. You're also minimized and the cost independent of complexity. This is very most important advantages with respect to the additive manufacturing. So irrespective of any complex geometry, the cost is not very. So that means every time you are producing a different kind of features based on your STL file. So that's why it doesn't matter with respect to the complexity, the additional cost may not be increased. So that's why it is greatest advantage. Whereas in conventional machining process, if you increase the complexity of the job, then you can go for higher degree of machining capabilities and also additional tooling and fixtures are required to hold the component in a certain position to manufacturing the components. Whereas in this case, it is not required. So there are 8 stages already you have discussed in previous faculty members. So I don't want to extend further, but you can also see the various stages how you are going to develop the component for end user applications. So this the component you are going to generate based on your idea or based on your previous experience. So that geometry you can generate in the CAD environment, then it can convert it into STL file. Then again your the file is transferred to AM machine. So this file is only compatible with the machine, not your CAD file. So STL file is a combination of 2D geometries, stereolithography file. So each layer is a 2D geometry. Then you can set the parameters according to your requirement. Then you can build the component. Then you can remove the component from the substrate. Then you can go for post processing. Then you can use for end applications. So interesting is next slide is very interesting. So you know the how to produce the component through additive manufacturing process. So initial stages you need a CAD geometry, then it will be converted into a scale file. So many stages are required to complete this object. Okay, fine. So I have different manufacturing processes. For example, I have CNC facility with high capability, that is 6-axis vertical milling machine. CNC milling machine is available with us, and also additive manufacturing facility is also available. Then if I give a component to you to produce this component with certain materials, then you can select which process is suitable for this type of material and also component. For example, this is a cup made up of ceramic material which can hold hot fluid. Now I want to generate this component through any one of the process. Then I can see the pros and cons for each and every process. Then I have to select the best one among two. Then only you will be the good manufacturer or good designer or good production engineer. So if I give it to layman, he can choose any one of the initial period. He can choose any one. And over a period of time, may also knowing, so this process is not suitable for this kind of material. So sometimes ITA guy is more knowledgeable than, we can say, faculty also sometimes, because he is always experienced with the machine, experienced with the material, experienced with the process. So he can have a better understanding, and he can also give a better solutions to the industry. A simple example, F.W. Taylor is a machinist. So he came up with that high position because of his hard work and experience and implementation. So coming to this ceramic material, and I have two process. Then ceramic material, just you can go for CNC, for example. Then you need a cutting tool for machining of ceramic material. So definitely you can go for carbide tools, which is harder than your ceramic material. Then if you want to generate this kind of object, then you need different axes. Then finally you can generate the component. So once you know the basic machining process, because ceramic material is a brittle material, so if you want to machine it, the chips are discontinuous nature. So a lot of energy is required to remove the material. So even if you are supplying the sufficient amount of energy, then after machining, you may not get the good surface finish because it is a brittle material. Interrupted cuts is taking place. Due to that, you can get less surface finish. But customer requirement is high surface finish. Then you don't want to buy your component, even if you are taking a lot of risk to produce this kind of object through CNC machining process, but you may not succeed to sell the component to the customers. Then if you apply the same, produce the same component through additive manufacturing, So it becomes very easy. Just you are melting the ceramic material, applying your laser beam, then you can melt it and just you can uh, layer by layer, you can deposit it so that you can able to generate this component. So what do you understand by this example? Ceramic materials. That means in general, brittle materials cannot be possible through CNC machining process because inherent property of the material leads to inaccuracy in the surface finish or any other geometry also. Whereas additive manufacturing, it is very simple job to complete this kind of object. So with respect to the material, you can choose which process is suitable for the particular material to get your required dimensions or surface finish or properties, etc. Similarly, I can give another example. If I take aluminum alloy, for example. So aluminum alloy is a ductile material. Okay. Then you can go for CNC and additive manufacturing. So both the process are possible to produce this component. But additive manufacturing process will give more time to complete the process, and also it leads to deterioration of mechanical properties because of porosity existing in the component. So if you apply CNC, because it is a ductile nature, then you may get a good surface finish and good geometry accuracy, then you can able to produce the component without much loss of properties. So in that case, you can go for CNC. If you don't have any knowledge of the metallurgy, then you are the failure person in additive manufacturing of aluminum alloy components. Then coming to the complexity, suppose if it is more complex nature, for example, you take this component. If you are talking about at the bottom portion, it is gradually increasing the inside diameter. So once it is comes to this stage, then again the geometry is vary. So if you want to produce this component in CNC, normal CNC vertical milling machine is not possible. You can go for 6-axis milling machine so that you can able to generate this component. So for that you need a large volume of the initial components required to produce this component through CNC machining process. Whereas additive manufacturing, each layer is a unique nature, so you can able to generate the component very easily. So if it is a complex structure, more complex, which is not imagining sometimes. For example, people are working in micro channels. The channel is not a same cross section throughout the component. It can vary depending upon your applications. So if it is more complex nature, that geometry is inside to produce in the component, it is very difficult task in case of CNC machining process. Whereas additive manufacturing, it is very possible. So irrespective of any complex geometry, the additive manufacturing is very useful and also reduce the cost involved during the process. The speed, just you can see the speed of the machining process. So that varies from material to material and the complexity. Suppose if I take a simple geometry, cylindrical rod, I want to produce through CNC, I want to produce additive manufacturing. So after experience, after completion of this course, if I given to you this component is made up of CNC and AM, then you can choose which will give the better properties. Naturally, CNC will give the better properties than additive manufacturing. So if it is simple geometry, the machining process is very feasible solution than additive manufacturing because it takes a lot of time to produce the component. To produce the component is not a job. To produce the component within the stipulated time is also important. And also accuracy is also important. So coming to the next aspect, the programming. So CNC and additive manufacturing, in my perception, there is no much difficulty in both the cases. Then coming to the last one, we can define additive manufacturing as a 3D printing. But CNC, we cannot call it as a 3D printing. Even though you are producing the third dimension component, but you cannot say it is a 3D printing process. Why? Because so in CNC, some portion is folding. That portion after completion of your entire component, that portion you have to remove or you can change the geometry according to your requirement. At least one change of setup, minimum one change of setup is required in case of CNC machining process. That's why it is called 2.5D process. Whereas additive manufacturing directly can produce third dimensions without changing the setup. Only thing is you have to separate the component from the substrate. That is only the option. So that's why additive manufacturing is a 3D printing, you can say. So this slide will give you an idea about the difference between conventional or computer numerical control machining process and additive manufacturing process, where we can apply this kind of process to produce certain component. So if you understand very well about the particular slide, you will be the good additive manufacturing engineer. You can select your problem, you can define your objectives to do your research work or development of any component. Yeah. So how much time you are going to save? So this is the total time you are going to save when you are using 3D printing process or additive manufacturing process. In ordinary conventional way of producing the components, conceptual design, detailed design, engineering analysis, prototyping, tooling, production. So after producing the component, so when this component is applied to any application, functional requirements. So if the component doesn't meet the functional requirements, again you have to change your designs and again you have to do the process. Even if you are not succeed in the second stage, again you can go for the first stage. Like that, you are repeating n number of trials, then finally you may be succeed. So same principle you can apply here, but only change in the design in your CAD environment. That is only the problem to change your designal aspects. So remaining thing is same, only you are going to change in the, that is also in soft mode, then so that you can save this much of time for generating the successful component through additive manufacturing process. Yeah, this is sustainability. So once you have developed the component through additive manufacturing, then you can also see the sustainability of the component. So this is now the people are talking about sustainability additive manufacturing process. How your component is sustained, how your process is sustained. So sustainability in terms of functional requirement, in terms of global requirements also. So when you are talking about the global requirements, how much energy is you are consuming for producing the component through additive manufacturing process. So whether it is less than the conventional energy or higher than the conventional energy. So then only you are sustainable. Otherwise, your process is not sustainable. Then it is very so once you are producing the component through additive manufacturing process, whether it is going to affect the environment or not. Yes. If you are using powder bed additive manufacturing process, it creates pollution. So that leads to a global environment problem. Okay, the customer point of view, you can see that the component is very nice and can also appreciated by the customer, well and good. Then over a period of time, you are going to harmful effect to the environment. Then after that, after some time, your process cannot be used for because of the global environment problems. So that's why you have to select the process and what is the feasible solutions, how it can be sustained over a period of 20 years or 30 years. That you are going to see. So with this chart, you can have an idea of compatibility between your customer demands and your requirements, and also leads to sustainable additive manufacturing process. So how much production you are going to generate through additive manufacturing process? Then what is the shape and size of the component? Then what are the materials you are going to use for building the component, whether it is a polymer or metal or ceramic? Then how much volume you are generating, at what rate you are producing the component? Then is it customization or part consolidation or geometry complexity? Like that, you have to think. Then once you are having these minds or objectives in your mind, then is aim is suitable or not? Okay, because the topic is aim, okay, I can say aim is suitable for your objectives. So once you can decide to go aim is suitable, then what is the size of the part you are going to generate? What is the duration? How much time is required to complete your component? So what is the surface finish requirements? Then what are the tolerances? So this is also very important. FQ, we can say in additive manufacturing, fit function forming form. Fit function form. So fit is the tolerance. So without tolerance, you cannot meet the two components. What type of fit is required to join these two components? Then form. How to produce this component? And what type of feature is required to generate this component. Then function. Once you are producing the component, it should not be ideal, no? It can be applied to any applications. So what are the functional requirements of this component? So that F cube, it is not only applied to additive manufacturing, any problem, even in our life also. F cube is very important. 3 Fs, 3 Fs, or F cube, you can say. So what is the feature size? Suppose I want to generate nano feature on some portion of the component. Is it possible? Then you can see suppose if you go for powder bed fusion process, your particle size must be a nano level, lesser than your feature size. So I want to produce micron feature, but you are taking the powder particle more than your micron feature, you may not produce. So that's why engineering knowledge is required. So I want to produce the miniature, let us say 20 micron feature. Then I have to select the powder less than the 20 micron, not above 20 micron. So those guidelines or those informations are necessary to produce a particular size of the component. Okay, once you are producing the component, what is the life of the component? How much life you are expecting? For example, if you want to buy automobile, the 15 years life, how do you decide the 15 years life? And what factor you are deciding the 15 years life? Okay. So that is fatigue behavior of your shaft, because it is when you are running the vehicle, the propeller shaft. Let us say if you take four wheelers lorry for example. So always it is continuously rotating while it is running. There is torsional loads, bending loads, and fluctuation loads. So each material has its own life depending upon your imposing criteria. So if you are static, life may be better than in dynamic conditions. So like that, depending upon your applications, you can decide the life of the component. So once you have decided what properties, so strength, stiffness, and hardness. So these are important. How much strength you are going to get. Then what is the hardness? What is the stiffness? So every additive manufacturing component, we are getting more strength. More strength means here people are confusing. I am getting strength is that is 300 megapascal. What strength you are looking for? There are two strength. One is ultimate tensile strength and yield strength. So ultimate strength is very important for designing of any component. So that is your strength of the component, not UTS. So UTS is no way concerned in the design aspects. Your strength is yield strength only, because up to that limit of uh, megapascal, you cannot yield. That material cannot be yielded. So once yielding occurs, then you are losing your properties. So your life is going to decline trend. So that means the additive manufacturing, especially additive. This is I'm going to talk in next session. All the additive manufacturing components, you are expected more ultimate tensile strength than any other process. So what are the reasons that I will explain in the next session? But here the concern is yield strength, not ultimate tensile strength. So suppose if you are increasing by ultimate tensile strength per 10 megapascal or 30 megapascal, so you are the best engineer because you can save a lot of material. If you are improving the property of let us 10 megapascal, you are saving a lot of material. The weight of the component, weight of the entire structure is tremendously reduced. So this is useful for your aerospace applications and defense applications. Always they are looking for high strength to weight ratio. High strength to weight ratio. That means your component must be high strength. At the same time, your weight should be very low. Then go for preliminary selection of feasible machines. So what are the machines are available? So once you are having this kind of analysis, then you can search for what are the feasible machines are available in and around you. So once you are selecting based on your component, for example, I can give one example. Suppose I want to generate a miniature component. That component is useful for electronic applications. Then definitely I can go for powder bed fusion process only. Because if it is complex nature, that too miniature component, so only the solution is powder bed fusion process. Okay. So those options you can work out before selecting the machine. Okay, everything is fine. I have machine. I have the knowledge of the previous criteria. Then I want to build the component. So building the component perpendicular to this your surface plate, your substrate, or parallel to surface plate, substrate, or inclined to this substrate, also possible. So what type of orientation you are depositing the material? So that's we can call it as stand strategies. So many of our scholars are working in this area. How to maintain your strategy? So what strategy you are looking for? So it varies from material to material, and also not only the material. So it is also influence the cooling rate during after printing process. For example, if I give a one famous example, pin fin, for example, already many of our studied in heat transfer, pin fin. We are projecting the cylindrical pin on the surface of the carburetor, etc. That is extended surfaces. So if you are keeping the extended surface, heat transfer rate is more. So inside the engine, there is a lot of heat generation. That heat is extracted quickly from the material to the environment. Then only your life of the component is more. So like that, while printing also, if you change the orientation, this heat transfer rate is also going to change. That leads to difference in mechanical properties. So just you can see the normalizing and quenching, artificial aging. So these are the three different heat treatment techniques which can enhance the properties of the material. So normalizing it, just you can heat the material and kept in open atmosphere, then slowly cool down to room temperature. You are not having any control to rate of heat transfer. So in that case, your properties are lesser than artificial aging, artificial cooling. So same component heated to particular temperature and allowed to cool under controlled atmosphere. The rate of cooling and fixed. I can keep the component in its chamber, then rate of cooling is fixed. Then if you are keeping the rate of cooling is constant, then your properties are different from your normalizing component. You are expected better properties than normalized component. Similarly, I can heat the component, just I can put in the water or any oil bath. What is happening? Sudden cooling takes place. So when the component is subjected to sudden cooling, you are expected that the strength of the component is very high. Strength means ultimate tensile strength. Again, so you are not giving a chance to grow the grains. So if you take these three components, artificial cooling component is better properties than followed by normalizing, followed by quenching. So if you are talking about yield strength at the point, this is the order. If you are talking about only hardness, for example, hardness, you are the criteria. Then pinching component is a best one, followed by normalizing, followed by this artificial cooling, vice versa. So depending upon the applications, for example, I want to generate shoe brake, then I need much harder than the other components so that resistance to wear is increasing. So that life of the shoe is more. Then you can go for a quenched components. So that is one aspects you can also think of while doing your research work. Then spacing between one layer to next layer. How much you are giving space? Adjacent layer, not the vertical layer. How much space? Whether it is exactly touches the previous edge of the layer or just you can go down, overlap the previous layer, that is the 50% or 20% or 10%. Like lap joint, just you can think of lap joint. So how much distance? 1.5 times the thickness of the plate in welding lap joint. At 1.5 T you can keep it. So this is based on the previous researchers give a solution to us. So you should be minimum 1.5 times the thickness. If you are keeping more, there is no problem, but you are wasting your material. If you are keeping lower than 1.5 times, the strength is come down. So either this way or that way is not useful, but only the solution best release is 1.5 times thick. So like that, how much spacing you are giving? So if you are giving 1.5 times, that is overlapping. If it is more overlapping, it takes more time to complete your job. If it is less, somewhat lesser completion time compared to the previous one. So if it is still you are touching, sometimes may not be joined these two edges. So that is a problem for creation of void. So this is also depends on material to material. It depends upon flowability of the material and other physical properties of the material. So once you are identified, what is the time for your building the component? Okay, I can produce a beautiful component through additive manufacturing. The customer point of view, he doesn't bother about how much time you are taking for building this component. But your boss is bothered about you because you are using lot of time so that you can use lot of energy. The cost involved for producing the component is much higher than the other processes. Then immediately you can give a caution to you, say that you can look for other alternative solutions or you can minimize the energy consumption during the process. So like that you are estimating the cost of the component. Then finally selection of best machine. So based on all these criteria, you are thinking of the best possible solutions. Then coming to the, yes, you can see the, with this slide, I can give 5 minutes break. Then after that, we can go ahead for the remaining part of today's lecture. The cost, just you can see the graph. So this curve is injection molding, whereas other additive manufacturing, for example, stereolithography, fusion deposition modeling, laser sintering, completely horizontal line. So there is intersection point. So that is known as a break-even point. So even after using, that is, let us say 6,000 component. So if I want to produce 10,000 component through additive manufacturing, okay, you can produce, but the cost involved is more than your injection molding process. So if the problem is feasible and also a better solution than your additive manufacturing, you don't shift your process to additive manufacturing. So if you are still surviving with this conventional way of producing the components, don't look for additive manufacturing components. Okay, if the geometry is complex nature, then definitely you can go for additive manufacturing based process. So I can give 5 minutes break. Now the time is 10:30. I will meet you again 10:35.
Sir?
Hello?
Yes, sir.
Yeah, yeah.
Sir,
We'll give 5 minutes
could
break.
slide mode is not visible, sir. Only PPT is visible, sir.
Slide mode.
Sir.
Yeah, yeah. I changed the Mode
Okay,
to slide mode.
okay.
No problem.
Any issue, sir?
Yeah, no issue.
Okay, sir. Okay.
Just I have changed it. Just hold on.
Okay, sir. Okay.
No, I had given 5 minutes break actually.
Yeah, now came, sir.
Now it's okay.
Yes, sir. Fine, sir.
Yeah. So after 5 minutes, I'll start again. Today evening, what time the class will start?
Afternoon, sir.
Afternoon,
Sir. 12 to 2 is there, sir. Then 3 to 5, sir.
3 to 5. Okay.
Yes, sir.
So today I'll take 3 to 5. So tomorrow lab session.
Okay, sir.
Morning in my slot because tomorrow I'm going to attend marriage.
Okay, sir. Okay. Right, sir.
So you can inform the students
Yeah, I
after.
will inform, sir. After my session,
Yeah.
I will inform, sir.
Hello?
Okay. Yeah, I will inform, sir.
Record just better. Start అయినా మీరు ఓకే రైట్ మంచి అది పంపించాను వచ్చిందా ఫైల్ ఏమన్నా
Which one, sir?
మిమిక్ సాఫ్ట్వేర్ అది పంపించాను
సార్ వాళ్ళు అడుగుతున్నారు సార్ బట్ అఫీషియల్ గా ఏం రాలేదు సార్ ఇంకా
ఓకే
అదే
నేనైతే
సిపిసి మీటింగ్
నేనైతే
అవ్వాలి సార్
లాస్ట్ 2 days క్రితం పంపించాను ఫైల్
అదే సార్ మోస్ట్లీ ఎవరి వెగ్నెస్డే సిపిసి మీటింగ్ కండక్ట్ చేస్తారు సార్ అది అయిన తర్వాత వస్తుంది
ఓకే ఇంకేమున్నాయి మనకి
సార్
కొనాల్సిన ఏమున్నాయి
అది పౌడర్ ఏమైనా కొనాలి సార్ మనం
ఆర్డర్ ఏంటి
పౌడర్ మెజర్మెంట్ సార్
ఎంత ఎంత అవుతుంది ఇది అప్లికేషన్స్ ఆఫ్ అడిటివ్ మ్యానుఫ్యాక్చరింగ్ you can find many applications nowadays from general to real applications, prototyping, tooling, metal casting, architectural, dental, and especially direct art production, aerospace, automotive, medicals, etc., and even jewelry items also. So these are the components produced by additive manufacturing process for aerospace applications. Now coming to my actual topic is non-beam based metal additive manufacturing process. Uh, so additive manufacturing process, we can define melting and deposit layer by layer so that you can get the component in third dimensions. Uh, Likewise, you can also develop the component in non-beam based additive manufacturing process without melting. That is also possible method to produce 3D components through non-beam based additive manufacturing process. So in this, I'm giving one example. For example, flush door is a we can say non-beam based additive manufacturing process. So the flush door inside and outside layer having a good surface finish and good strength, but inside the material not that much quality because it doesn't require. So only you need to maintain the sufficient strength is enough for the particular door. So in between, they can apply adhesives so that joining takes place between one sheet to the another sheet, so that finally it come up with a 3D type of object, so which we can call it as flush doors. That is one example. Then another example, just you can see metrology lab. We can also keep slip gauges one over the other to get the required height. So each slip gauge is highly polished surface. You can see your face also on the slip gauge. Why it is required high surface finish? Because high surface finish is directly proportional to energy. That is, you can call it as surface energy. So if it is having high surface finish and high surface energy, so that energy required to join other components, that energy is sufficient to join, creating a bonding between the other components. So just you can keep the slip gauges perpendicular to each other initially, just you can rotate one over the other so that the vacuum bond is created between these two. So like you are maintaining one over the other, it is also a 3D manufacturing process. So initially 2D geometry, that is thickness is very small. Once you are building one over the other, then finally it requires certain amount of height. So it is in the form of layers, you can get the final components. So that is also comes under non-beam based additive manufacturing process. So like this, we can also explain how you are converting your welding process to additive manufacturing process. Yes, you can see. So both friction stir additive manufacturing and additive friction stir deposition are intensive process that involves severe plastic deformation at high temperatures. Yes, you can see. So in the friction stir additive manufacturing, there is a tool which consists of a shoulder and a pin. So this will be rotated at certain RPM. And once the pin is inserted between the materials, the shoulder, the bottom of the shoulder is contact with the top surface of the layer number 4. So once you are rotated, and also you can apply the downward force at the initially the bottom portion of the pin pierced through the material because heat is generated due to friction. So that heat is transferred to the material and reaches to its recrystallization temperature, where softening of the material takes place. Then at the moment you can apply the force, that pin will be inserted into the material. So once the pin is completely go down, then the another portion you have the shoulder. The shoulder is contact on the top surface of the layer 4. Then still it is rotating because this is the stationary, this is rotate 1. So due to that, lot of friction is developed. That friction causes to increase the temperature bottom of the shoulder portion of the layer 4. Again, that portion reaches to its recrystallization temperature, then you can move the tool this direction. So just you rotate anti-clockwise and moving in this direction after reaching the recrystallization temperature of the material. Then the importance of the recrystallization temperature is at that temperature the grain boundaries are weaker. Yes, you can move the material according to the force direction. This principle we can apply in the farming process. So same way you are reaching the recrystallization temperature and also rotating as well as moving the movement of the material from this side to another side. So like that the material movements takes place and fill the backside of the pin. So the material movement takes place and fill the gap at the backside of the pin. That's why the welding is formed. So the material movement is that is material flow is very important role. So the material flow is the function of various parameters like rotational speed, welding speed, and tool diameter, pin diameter, tool material, and work material. So many factors which governs the your material flow. If the material flow is improper, then you are not accommodate the sufficient material at the backside of the pin. So that leads to a creation of slot. So when you are talking about slotting operation, so just you are removing the material from the stock, that after removing it becomes a slot. So instead of doing removing the material, we are trying to accommodate the same material at the backside of the pin. So even it is happening in the friction stir additive manufacturing if you are not providing sufficient heat generation. So if you are not providing sufficient heat generation means that indirectly you are not giving sufficient rotational speed and welding speed. That leads to creation of slot. That is improper material flow. Why improper material flow? You are not giving sufficient heat to that material. So it may not reaches to recrystallization temperature. So when it is not reaches, whatever the material, yes, movement of the material could not be happen. So that is very important aspect in friction shear additive manufacturing process. Yeah, come back to this slide. However, there are significant difference between them. First one is a hybrid, both additive and subtractive process. Sheet lamination process involve welding that results in microstructure with cyclic variation, whereas the other is purely additive process that deposits a new track out with each pass, with each individual layer undergoing the same type severe plastic deformation during deposition and reheating afterwards. Additive frictions in deposition can lead to much more homogeneous microstructure. So just I am giving comparison between these three processes as per different criteria. For example, as per ASTM classification, the ultrasonic additive manufacturing, the thickness of the sheet is the order of zero point 0.1 mm thickness is required. And also, it requires good surface finish. Whereas friction stir additive manufacturing, minimum 1.5 mm thickness is sufficient. Whereas additive friction deposition, there is no sheet. We can do some other techniques to deposit the material over. Then hybrid process, you can also implement both additive as well as subtractive. Then you can call it as a hybrid process. So it is possible to include both additive as well as subtractive process in the case of ultrasonic additive as well as friction stir additive process. Here only additive process. We can also accommodate, but doesn't that much essence is required. So resolution limiting factor subtractive process. This also subtractive. This is based on tool geometry. We can also define the properties. The temperature relatively low, relatively high in both the cases. Whereas in this case, as I said in the beginning of this lecture, so very low temperature is used for an ultrasonic additive manufacturing process. The microstructure you can see before and after additive manufacturing, it is similar to pre-process, that is similar to your base material. Whereas in this refined and equaxed steel zone and refined equaxed gel. So you can also modify the grain structure in ultrasonic, in friction stir additive as well as additive friction stir deposition process. So comparison to ultrasonic additive manufacturing, additive friction stir deposition is a fundamental different in that it is a material deposition process rather than a sheet lamination process. So you are adding a material, deposited material, not a sheet is directly attached to the previous sheet. So that is sheet lamination process. In addition, the microstructure resulting from the intensive friction stir process is dependent on dynamic recovery or dynamic recrystallization, whereas the gentle ultrasonic process gives a similar microstructure before and after fabrication process. Both friction stir additive manufacturing and additive friction deposition are intensive process that involve severe plastic deformation at high temperature. So here, once material reaches to requisite temperature, then you are applying the rotation as well as moving the tool in the direction of process, shearing action takes place. That is, intensive plastic uh, deformation takes place. Due to that, refinement of the grains takes place. However, there is significant difference between them. One is hybrid, both additive and subtractive. Sheet lamination process involves welding that results in microstructure with cyclic variation, whereas the other is purely additive process that deposits a new track with each layer. So for widespread implementation, Metal AM needs to process a series of attributes such as affordability customers, convenience, and easy of use, energy efficiency, environmental friendliness. This is very important. So what we are talking about in powder bed fusion process, it will affect the environment because a lot of energy are utilized and smokes are coming up during the powdering process. So that will harmful to the environment. Whereas in this case, there will not such gases because it is below the registration temperature only. We are not reaching the melting point temperature. There will not be any gases at all. So wide applicability to engineering materials, compatibility with the measure technologies, reliability of part properties, etc. So it is a solid state process. There is no melting of the material. As I said, there are different layers of similar materials of similar melting point temperature. You can initially pack them. Uh, you can see that the surface of the plate should be uniform throughout the area so that you can avoid the voids between the two layers. Suppose if it is uneven surfaces, there will be void. So that void will be present after the process also. It becomes a reduced one, but defect should be as it is. That's why the surface which you are going for the efficiency additive manufacturing, the surface is very most important criteria. So once you are keep the all four layers, yes, you can rotate this tool and touching the bottom portion of the pin after some time, that is a dull time, then it reaches to the same temperature, then you can plunging through the all the layers and by applying the downward force so that the shoulder will be contact and again it rotates, it reaches to the temperature, then you can move the tool in this direction so that the joint is formed. So like that, just you can see this structure. It is an additive manufacturing process. So before making this, so it is an individual one, the layer 1 to layer 4 are individual. Then after making this, it is a combined form so that you can get different uh, materials of similar melting point temperature. You can also see the variation of the microstructures and variation of the properties from the top to bottom also. So this region, suppose you may have a question, why don't we extend to whole width of the plates? Yes, it is possible. We have done some trials on extend to this surface also on both the sides so that you can get the 50% overlapping should be done or 40% or 20% overlap so that you can reduce the processing time so that you can able to join the components very easily. So with a limited time, you can able to produce a large size of the components. That is an advantage. So better understanding this process, just you can see the one video. So that is the plunging stage. The movement of the material takes place from here to there and the back side of the pin. The entire width is become a additive manufacturing component. Yes, to fix the cutting tool, that is milling cutter, to remove the unwanted material, that is known as the subtractive process. Yeah, this is the final component. So how it is very simple to generate this kind of object through friction stir additive manufacturing process. Yeah, coming to next process, additive friction stir deposition process. The difference between the tool is in the previous case it is solid one. Now here the hollow one. Just you can insert the filler material which is going to deposit on the substrate. The machine is same, the principle is same. Just you have to alternate your tool design. So without pin, just you are rubbing against the substrate, both the shoulder and the filler material. Because the filler material melting point temperature is lesser than the solid material, then it is early reaches to regression temperature. It is far away from that position, so there is no yielding occurs, whereas yielding is occurs in the filling material case. Just you are rotating as well as you are sending the filler material by applying sufficient amount of downward force so that the metal is deposited onto the substrate. So this is known as additive friction stir deposition process. So using the principle of solid state welding or friction stir welding, just we can heat generation by the expense of the friction. So that leads to recrystallization temperature of the filler material early so that you can deposit the material onto the deposit substrate. So yes, you can see these two pictures in both friction stir additive manufacturing, additive friction stir deposition. So I want to generate this component. Initially, I have to make all the sheets into together. Then pin is inserted between the all the sheets. Then I try to rotate the shoulder and moving perpendicular to the slide so that the material movement takes place from here to here and fill the backside of the pin so that I can generate this type of component. Whereas in other additive friction deposition, all a shoulder, you have a filler material which can be deposited on the substrate so that because of the friction, the material is deposited on the substrate. So just you can see this chart graph, you can understand how much it is useful for industrial applications. So on the x-axis, you can see the building rate, and the y-axis amount of accuracy in terms of microns. So you can see the powder bed fusion process very small in building rate as well as accuracy level also very small. Then compared to DED, direct energy deposition process, where energy source is directly contact with the powder particles or wire, just immediately melted and deposited on the substrate. So that gives more idea, more building rate as well as more accuracy than powder bed fusion process. So this is very advantage compared to the powder bed fusion process. This we will going to discuss in the next session. Then coming to the our additive friction deposition process or friction stir additive manufacturing process, you can see there is a wide rate, building rate as well as accuracy. Because within the stipulated time, you can able to generate large size components especially aerospace applications. The material may be titanium alloys as well as all aluminum and magnesium alloys are to be done through friction stir additive manufacturing process. All bullet train panels, people are doing uh, panels which were made by titanium alloys, uh, doing friction stir welding as well as friction stir deposition process. That will give more high strength to weight ratio for high speed trains like bullet trains. So this much of advantage when you are talking about accuracy as well as building rate with respect to the additive friction cell manufacturing process. So additive frictions deposition, you can also produce not only similar materials, you can also produce uh, anisotropic materials. That the variation of properties along the dictated direction, it is also very simple task to complete this through these techniques. This is one of our scholars' work. So he wants to develop a functional graded material through this technology. So first of all, you should understand what is the functional graded materials. The properties are varying from one location to other location with respect to the uh, thickness or with respect to the length, whatever it may be. In particular direction, the variation is occurs. The property. Those materials comes under functional graded materials. Why we need? For example, you want to develop a shoe brake. So outer layer, which is always contact with the rim of the wheel when you are applying the brake. So that layer should be very harder than the bottom layer. Why we need? Why not total component should be a harder one? Okay. So just you can, if you are applying the brake, you are trying to stop the vehicle. So whatever the kinetic energy, that will be converted into heat energy. So that heat will be transferred to your rim of the wheel as well as your shoe brake. So when your heat is transferred for a longer period, the material properties are come down. So whenever the material exposed to temperature over a period of time, the temperature stresses are induced. So that leads to degradation of the properties. So then your life of the shoe is decreasing. So immediately the worn out takes place, then you want to replace the shoe. So for improving the life of the shoe, then you have to think of alternative solutions to improve your life of the shoe. Only wire top layer is required harder. The bottom layer doesn't require. So if you go for softer material in the bottom side, whatever the vibrations when you are applying the brake, those vibrations can be absorbed by the material when the material in soft condition, that is tactile nature. So if it is brittle nature, it will not absorb at all. So ductility is more important at the bottom portion than the top portion. So if you are going for functional graded materials, the top one is highly brittle, and then below that slightly lower than brittle material. So if you are decreasing the brittleness, indirectly you are increasing the ductility, or bring down to your versional material ductility. So with this background, why don't we try with our facility to produce functionally graded materials? So he was successfully completed. He got good publications on these techniques. So initially, what we do is you have to make a groove, and you can fill your reinforcement particles that is, let us say silicon carbide, then you have to apply the processing. Then after that, yes, you can see this red color will have a composite material. It's a mixture of your virtual material and the reinforced material. Then again you have to make a groove. Then again you have to fill the powder. Then you do apply the process. Then you are getting the second green. So this powder concentration is different. This powder concentration, because you are adding some more quantity. Already this entire one is a composite, but you have to make a groove and you can fill the powder quality. The concentration is go on increasing from the top to bottom. Sorry, bottom to top. So once you are doing like this, the second variation is taken place. Like that, you have to make a groove and you have to make another tool which is equivalent to the length of the groove. That's why you are changing the different tools of different pin lengths. So like that, you have to produce different combination of reinforcement from the top, bottom to top. So just you can see the observation of the microstructure at the region, this region. Yeah, this is SIC region. Then this is still higher concentration than bottom region. Then still more concentration than top region. Then when you go for analysis, that is phase distribution in the different regions, just you can see the phase distribution of silicon carbide. The top one is the region 1. We have 14.03 plus or minus 3 silicon carbide percentage, whereas region 3 you have 9.18. So there is a 5% variation of SIC from the region 1 to region 3. So this shows the volume of the reinforcement is varying from top to bottom. So the more quantity of SIC, more hardness. So indirectly, your hardness is higher than this one. So you can also see the hardness distribution from region 1 to region 3. This is slightly higher harder than this one. So further improvement also done. He has completed not only one pass, he has two repeated pass is completed, second pass and third passes. So after preparing this one, he has to complete again, do it without any additional reinforcement. Yes, you can apply the techniques so that that second pass, third pass, so that further refinement takes place. Then that's why improvement of the mechanical properties. Let us say 150 HP. Initial one is 120 to 150 HP. 30 HP is improved by doing this process. So this part becomes a functionally graded material product. So you can also extend it to other region with the same principle. So entirely this block becomes a functionally graded material. So like this, you can get the functionally graded materials by depositing the reinforcement with different compositions so that you can able to get the variation of the properties from in terms of directions. Yeah, this all the information related to what I speak just now regarding heat generation like that. The solid state nature, the peak temperature of an additive efficiency deposition process normal ranges from 60 to 90% of the melting temperature. Because of the absence of cooling, melting parts do not suffer from the issues associated with the rapid sublimation. Especially, we are reducing a lot of problems during this process: porosity, hot cracking, elemental segregation, dilution, and finally dispersed oxide particles and residual stresses. The low porosity residual stresses is the dispository part. Like that, you can have different combinations. Just you can see one of the uh, information from the source. They have made copper to tantalum, copper to niobium. Just you can see the physical properties of copper and tantalum and niobium. Very large difference in melting point temperature, even though you are able to successfully weld it through these techniques. So this is very useful for industrial applications. During welding or during melting process, it's impossible to get these kind of uh, combinations. With this combination, with this technology only, you can able to successfully, irrespective of difference in melting point temperature, you can able to successfully complete this job. So speed and scalability, you can also build the large parts also. Only thing is you can have a big machines. Then you can see the non-beam flexible feed material and scalable benefits of the additive friction deposition process, no melting, low energy, low cost, cast alloy, consolidated powder, high building rate, etc. Then refined grains because of the dynamic legislation, no certification. Just now we have discussed all the problems can be avoided through non-beam based additive manufacturing process. So I cannot say this is the best process. Each and every process has its own limitations apart from many advantages. Uh, so, so the limitations uh, mainly the buckling issue is when you are going up to certain height. Beyond that, buckling is a problem because always you are applying downward force. Without force, you cannot able to build the component because we need friction. For that, you need sufficient amount of downward force and the firm contact. That's why the buckling is a major issue in this case. And also another problem associated tooling is also very important because always it is rubbing against the stationary surface. Due to that, wear and tear takes place. Due to that, every time you are going to change the tools. So that's why the people are, our students also suffering a lot because they have to make the tools. That's why additionally, so initially you have to make 10 tools at a time so that you can change frequently depending upon the situation so that you can able to complete the job within the stipulated time. Then I can time is 11:15, then 11:20. Now this I think it may be go for discussions. Then after that we can wind up. Then next class I'm going to give on the remaining part of ultrasound additive and remaining part with respect to the challenges in metal additive manufacturing process. Okay. Now it is open for discussion. You have any queries, just you can uh, have a discussion during 10 minutes.
Over, sir.
Yeah,
Yeah. Okay, sir. Thank you, sir, for giving a brief overview of this solid state additive manufacturing process. And with respect to the real time examples, you had given a very broad insights of this metal additive manufacturing, sir. Thank you very much, sir. Participants, if
thank,
you have any queries, please directly unmute yourself and ask the professor, or you can put it in the chat box also. Yeah, any queries from the participants regarding this metal additive manufacturing?
Yeah. If there are no queries,
Yes, sir. Okay. Yeah. If there are no, yeah, one query came, sir. I think.
yeah.
Sir, is there any
Is-
proven parts available with respect to friction stir additive manufacturing?
Yeah, number of parts are available. I've shown one video, no? You can make it, but you can apply some subtractive process also, addition to this. We have developed the component, which I shown you that functionally graded materials. I have developed the component also.
Any other queries from the participants? Sir, one more query at NIT Warangal. Does the sample facility available, sir, with respect to friction AM?
Sample facility means
Like
cannot
preparation of
understand.
FSW with AM, is it available? I think he is asking, sir.
Yeah, it's available, no? It's
Yeah,
available.
we are having a 3D printing. Also, we are having FSW.
Yeah. Both the facilities are available. Metal
Yes, sir.
additive manufacturing, powder bed fusion process, as well as friction state additive manufacturing process also available.
Yeah.
Yeah. Thank you.
Thank you, sir.
Yeah. Thank you. Thank you, everyone.
Yeah, I will end
Uh,
this session and will give a break at